Okay, as we look at the last couple parts of this problem, we are now told that ammonium ions react with water to form a solution with a pH of 4.827. We're given our reactants here, the ammonium ion and water. The first part of this asks us to complete the reaction above by drawing the complete Lewis structures for both products of the reaction. So complete Lewis structures for both products. Okay, as you think about what's going to happen here, do we think that the ammonium ion is going to act as the acid and be the proton donor, or do we think the water molecule is going to act as the acid and be the proton donor? As you think about the ammonium ion, it has to be the proton donor. It can't accept any more protons from water. It's already got its complete valence level, and nitrogen always follows the octet rule. So we're not going to have sort of 5 hydrogens sort of flying off the nitrogen here. So it's got to be the ammonium ion donating to the hydrogen ion. So what we're going to have left after we donate our proton here is going to be NH3, and after this gains a proton, it's going to be H3O plus, or the hydronium ion. Now, if I just wrote this, I'm getting 0 points because we're asked to draw the complete Lewis structure, and these are not Lewis structures. So as I think about drawing my Lewis structure, it's going to be nitrogen is going to go central here. I'm going to surround it by my 3 hydrogens. And then I'm going to have that lone pair of electrons on that central nitrogen atom. And then the hydronium ion is going to look very similar in terms of the geometry. Don't forget to encompass those Lewis structures that are ions, like the hydronium ion, in parentheses and include its charge outside of it. So that's it for this one. You get a point for drawing the correct Lewis structure for ammonia and the correct Lewis structure for the hydronium ion. All right, now as you look at this last problem, it's pretty involved. It's asking us to determine the number of moles ammonium ions. And a lot of these acid-base problems will be working with the concentrations of hydrogen ions, hydroxide ions. We're going to be working with the concentrations that we see in the equilibrium constant expressions. And so if we can determine the concentration of the thing that we're looking for and recognize that concentration or molarity is equal to moles over liters, then we can ultimately determine the number of moles. So just some things to remind yourself of. A lot of the information that you need to solve these problems are given to you on the formula chart. Just recognize that those formulas, those equations are giving you oftentimes concentrations. So in order to solve this problem, the very first thing I want you to think about as we think about this equation is what the equilibrium constant expression for this equation is. Okay, so if I were to write the Ka for this equation, and now I'm using Ka because this is acting as an acid, a proton donor, we would say that we have the concentration of our products, which is the ammonia, times the concentration of the hydronium ion, H3O plus, over the concentration of the ammonium ion. And so again, if we can solve for this, the concentration of the ammonium ion, recognize that concentration is moles over liters. We're told that we're a 250 milliliter solution. We can figure out the number of moles from there. But how do we figure out what this is? So in order to solve for the ammonium ion concentration, we need to know what is the Ka, what is the ammonia concentration, and what is the hydronium ion concentration. If we know these 3 variables, then we can very easily solve for the ammonium ion concentration. Now, this is a problem where, again, there are clues in earlier parts of the question that'll help you solve this. If you look there to part E, we were given the pH of the solution. And remember, pH is equal to the negative log of the hydrogen or hydronium ion concentration. So I know what this value is. I'm told the pH is 4.827. So how do I solve for x? The easiest thing I can do, or the first thing I can do pretty easily, is just divide each side by -1. So we get negative 4.827 equals log of x. So essentially here, to cancel out log, or to solve for x, because we're working with common logs here, it's going to be 10 to the negative 4.827 is equal to x. We plug that into our calculator. You can find that button underneath the log button there. So negative 4.827, which gives us a hydronium ion concentration of 1.49 times 10 to the negative 5. And again, that's going to be our hydronium ion concentration, H3O plus. Okay, so this right here is the hydronium ion concentration. So we've solved for one of those. Let me plug that in here. So we get 1.49 times 10 to the negative 5. Now, because the ratio of hydronium to ammonia is 1 to 1, the concentration of ammonia is also 1.49 times 10 to the negative 5. We are looking for the concentration of the ammonium ions, and the only other thing we need now is what the value for Ka is. So how can we figure out what Ka is? Well, once again, our formula chart is going to come to the rescue here. We can use this equation here that relates Ka and Kb to Kw. So Kw is equal to Ka times Kb. Now we're trying to solve this for Ka, which means that my expression is going to be Kw over Kb. Now I know that Kw at 25 degrees Celsius is 1.00 times 10 to the negative 14. But what is Kb? Where do I get that information? We have to remember that this relationship in Kw here is telling us the relationship between the equilibrium constant of the acid and its conjugate base. So our acid is the ammonium ion. I wonder where I can find the Kb value for its conjugate base, which is ammonia. It's not given to me in part D or F. We have to go back to the very first part of the question. Remember this Kb value from the very beginning? That Kb value is the Kb value for ammonia, which just so happens to be what we're looking for to solve this problem. So if I use that Kb value from the very first part of the problem, I solve for Ka to be 5.56 times 10 to the negative 10. Now that is just my Ka value, so I come back over here. 5.56 times 10 to the negative 10 is my Ka value. So if I do a little bit of algebra here, I get 5.56 times 10 to the negative 10 times x equal to 1.49 times 10 to the negative 5 squared. So some quick help from my calculator here. 1.49 second e to the negative 5 squared divided by 5.56 second e to the negative 10 gives me an x value of 0.399 molar for my ammonium ion. Woo! Feeling really good about this, except then we realize, oh, it's asking us for moles of ammonium ions. And so as I think about what molarity relates to me, I know the concentration of the ammonium ion to be 0.399 molar. My number of moles, that's what we're looking for. The concentration, the volume is 0.250 liters. Don't forget to change that back to liters. Therefore, my number of moles of ammonium ions here is going to be 0.0100 mole of ammonium ion. Now, again, a lot of work here, so really important to box in our final answer. This was worth 3 points. Your first point comes from determining the correct concentration of the ions in solution. Your second point comes from determining the correct value for Ka, and then your third point comes from determining the correct value for your moles of ammonium ions. Again, no points if you show no work.